Okay, so in this particular lab, you are going to build a counter, a kind of counter, um, and that is part of the lab. Part of the lab is using sequential, finite state machine, sequential programming, making sure that you can do that. And part of the lab is making sure that you can use the 7-segment display on the basis board. So those are the main skills that you'll be looking at. So I want to talk first a little bit just about counting. And one thing to be aware of that a lot of people don't actually think about is, let's say that I define a number in my Verilog, like so I have this is not the one I want. Okay, so I have defined a number in Verilog as, say, a vectored signal 2:0. So let's say I've got my computer does not like everything that I'm trying to make it do. 2:0, and I'm just going to have this variable, I'm going to call it x. Okay, so what this means is that x is a 3-bit number, and when I write it, so this would be bit 2, this would be bit 1, and this would be bit 0. And that's what it means to have it as 2:0. And so when I write it like this is the way we read numbers. We read numbers with the most significant bit on the left-hand side. Now, computers sometimes do it this way and sometimes do it the other way. They don't really care. And so you could also have 0:2x, and that's fine. It just means that this is bit 0, this is bit 1, and this is bit 2. And either of those is fine. This way makes it correspond to the way we think of binary numbers. So if I treat this as a binary number, then with this in position 2, position 1, position 0, then this number is, that's the 1's place, the 2's place, the 4's place, this number is 6. So if I have in my code, if I define 2:0x that way, maybe it's a reg because I'm have it somewhere in an always block. If I have a line that has x equals x plus 1, and let's say I initialized x to be 0, remember this is a binary number and it only has 3 bits. So it would start off, if I initialized it to be 3 apostrophe b colon 0, 0, 0. So let's say I defined it like that. That means it's a 3-bit number, it's binary, and I don't need the colon, sorry. It's a 3-bit number, it's binary, and I'm initializing it to be 0, 0, 0. Then the first time it comes to this, the first time it hits this line, it would make x equal to 0, 0, 1. It'll add 1 to it just like it's a binary number. The next time it would make it 2, and then 3, and so forth until it gets to 7. Now if I add 1 to it from 7, it only has 3 bits to work with, so the next thing it's going to do is to go back to 0. So it has the mod already built in. I've seen a lot of times students try to say, well, if x equals 7, then x equals 0. You don't need to do that because it will automatically, if you add 1 to 7, it'll bring it back to 0. And that could be useful depending on how you write your Verilog. You might have noticed that there were, well, let's get back to the program. Okay, so that's just counting with binary numbers. You can just, in Verilog, you can always just add 1, and that just counts just in the normal sequence. But in your lab, you have to count with a not normal sequence. And we'll get to that in a minute. So, well, actually, let's go ahead and look at that part now. So, your lab is going to ask you to count 0, 2, 4, 6, 8, 1, 3, 5, 0, 2, 4, 6, 8, 1, 3, 5, 0. So that is going to be your sequence. So you'll notice one nice thing about that. 0, 2, 4, 6, 8, 1, 3, 5. And then it should go back to 0, 2, 4, 6, 8, 1, 3, 5. How many different states are there? 8. And that's nice because that exactly matches the number of states you can get with 3 binary numbers. So that part is handy. Now, when we do this with a finite state machine, we don't need to think about being all math and sneaky and coming up with some sort of pattern that these numbers fit. It doesn't matter if they do or not. We just are going to assign them to different states. So, but we'll get to that in a second. So the next thing that I want to look at is using the 7-segment display. So did y'all use the 7-segment display in 2741? A couple times? Okay. So when you look at the board, so here's the basis board. I can only hold it upside down because the cable is only so far. On the video refresh rate on, oh, you can kind of see it changing a little bit. So the 7-segment display, you have 4 different displays, and they are 0, 1, 2, 3, going with 0 on the right. It doesn't really matter. If you do this, if you go right to left or left to right, it does not matter for this lab. You know, so that doesn't matter. But the one on the right is 0. Now, a strange thing is that the board is designed so that only one of them can be active at a time. And I say that, but if you look at it right now, it appears that they're all 4 active. And that's because the board can change a lot faster than our eyes can. So if you refresh really quickly, it'll seem like more than one is on. But for this lab, you're only going to have one on at a time. I mean, it'll only appear that one is on at a time. So, and here's how the 7-segment display works. So you've got, first you will tell it which display you want. And you do it by sending a signal to, in your constraints, you have if you go, so there is, if you have not already found it, there is a nice template file that has, if you go to, I put a link to it in the SI resources. Constraints template, and this is just on the Xilinx site. It has, this file has all of the possible different things that are on the board that you could use, and so you can just cut and paste that and uncomment out the ones that you need. And the ones that you need for the 7-segment display is you have a section that is, and so you've got the 7-segment display. So you will need those 7 segments from 0 to 6. If you want to do the decimal point as well, you can, but you don't need that. But you also need, beneath that, you have AN0, AN1, AN2, AN3. By the end of the semester last year, I got to where I always named my variables exactly what was in the constraints file so that I never had to change variable names. I just came in here and uncommented them. And so this particular lab, I did call this A instead of AN because A is what was in the notes. But if you call it AN, all you have to do when you put this in your constraints file is uncomment them out. So you will send a signal for your A, and it needs to be a 4-bit signal. So you will have, you will define as one of your outputs, you'll define A or AN, however you want to define it, as a 4-bit signal. I did mine 3 to 0, so with the most significant bit to the left. And when you do that, what this does for you is when you set this, you're setting what display is active. And it is active low. So if A equals 4 binary 1110, that means display 0 is active. If A equals 4 binary 1101, that means display 1 is active, because this is 0, 1, 2, 3. So when you are telling it what number you want to display, you not only tell it what values you want for the 7-segment display, you also send it this value to tell it which display you want. Okay, so so that's what this chart right here is showing you, is the values, what the bits should be. And then there's an example right here. If AN is 4'B1101, then display 1 would be active. Okay, so you also have, when you look in your reference, when you look at the Basis 3 reference manual, when they talk about the 7-segment display, and this is also in your book. Okay, so here's the 7-segment display. The names that are here are CA, CB, CC, and up, so CA through CG, and the decimal point. And those correspond to the different parts of that 8. Let me show you what it looks like in your book. Okay, so the segments are labeled A, B, C, D, E, F, and G. So I just remember them when I'm trying to remember what pattern I want, that it starts at the top. The top is A, B, C, D, E, F, and then G is the middle. And then if you put in a decimal point, that would be an eighth one if you wanted to do that. And the way I like to do it is I like to set up a variable. You can call it C. I called mine seg to be lazy because that's what it's called in the constraints file. So seg, and I had that. And this is important if you want it to go in order, the same direction alphabetically as the numbers are, you'll want 0, 6. So when you define segment, if you do it like that, then that means that, now, that means, notice this is backwards from how I did the one before, but that's because when I'm thinking of this number, the way I think of it is not as a binary number, but I'm thinking of this is A, this is B, this is C, this is D, this is E, this is F, this is G. That's the order that makes sense to me. If you did 6 to 0, then you'd have A, B, C, D, E, F, G. And either way is fine. But to me, this way makes sense. And so if I wanted to get the value, or the what would make the number 7, then that would mean I would need A. It's also active low. So I would need A to be low, and I would need B and C to be low, and everything else to be high. So low is 0 and high is 1. So you put a 0 in the places where you want it to light up.
It's Rebecca.
Yeah.
We can't see your screen.
How long?
Or what you're writing.
How long has this been going on? The whole time?
Probably about 10, 12 minutes.
Oh, wow. Okay. It shows that it's sharing. Okay. How's that?
Can see it now.
You can see it now? Okay.
Yes, ma'am.
All right. Wow. Okay. I am so sorry about that. Okay. So that didn't make any sense without actually visualizing it. Okay, but hopefully if y'all did it before in 2741, it makes some sense. And I'm going to post this recording so you can go back and look at it. And so the idea is you set up, if you want to do it like me, and you can do it however you want. You can do them all as individual variables if you wanted to. You could have 7 separate variables and name them if you wanted to. And you just have to map them correctly in the constraints. And so in the constraints, whatever you decide is going to stand for your 7 segments. So if you use C, then these numbers should be C. And if you use seg like I did, it could be SEG. So this is where you'll put them. And you don't have to, I mean, you can do whatever you want. You don't have to do it 0 to 6 like I did. I just do that to be lazy, because then it matches what I've got here. And so seg 0 is mapped to what is called in your book A. So seg 0 is A, which is pin W7. Pin W6, 1 is B. And so that's how those are mapped. Now, you can only send one C at a time because it only really allows one display to be lit up at a time. But that's okay because in this lab, that's what you need to do anyway. Okay, so before I go to the next topic, I want to pause for a minute and see, especially for those of you who couldn't see what was going on, are there any questions? Okay, so the example that I have here on the screen that y'all weren't able to see, that shows how you would make a 7. You have zeros in the A, B, and C. And if I wanted that to show up on display 2, then I would have 1, 0, 1, 1 would be equal to A. I'd have that on display 2. All right. Okay, now moving on. Okay, so the next thing that I'm going to talk about is I'll talk about the case statement after we talk about the pre-lab. Okay, so let's figure out what you need to do for the pre-lab. And it's going to be very similar to what I'm going to do right here. I'm going to not do exactly yours, but you'll see how close it's going to be. I'm going to define a different sequence, 1, 3, 5, 7, 9, 0, 2, 3, 4, 5, 6, 2, 4. And I'm going to say this is the count sequence that I'm going to do. So I am going to have each of these be a separate state. Now, we can have this be a Moore machine because when I'm in state 1, I want the output to be, my output will have my C equal to the LED string. I'll just not, sorry, the 7 segment string. And A will be equal to the display. So my output is going to be the string that defines my my number, and A is going to be the display that it's on. So for each state, I have 2 outputs. The only input I have for this lab is the clock, because the clock it's synchronous. It's just going to go kind of by itself. I'm probably just going to show you here how to use the button for it. I might make a video to show you how to use the actual clock so that you don't have to press any buttons, but I'll probably just do the button here. And so every time you press the button, it will just advance. And so your state diagram is really going to be pretty easy. So you'll have a reset that when you start, you're going to tell it to start in, I'll call it state A. In state A, I would define as my output C equals to, for mine, it would be 7B 1 0 0 1 1 1 1, and A equals to 4B 1 1 1 0. So what that tells it, if I've mapped C to my 7 segment display and A to the thing right underneath the 7 segment display, then this tells it in display 0, put the thing that has, so it starts, this is 1, this is the first bit right here, and that one is high, so it's not lit up, and then this one is lit up, and this one is lit up, and none of the rest of them are. So this would say put a 1 in display 0. And so that is going to be my state A. And so my output, I would have C equals 1 0 0 1 1 1, equals 1, 1, 1, 0. I think I need another one there. And then from there, it should automatically go to the next state. Doesn't matter what the input is because this is supposed to happen on its own. So I'll call my next state B. And the next state is supposed to be the number 3. So the number 3 would have C equal to 0, 0, 0, 0, because I'm getting this one, this one, this one, this one, and then 2 1s, and then a 0 for the last one. And then A, I'm supposed to go to the different displays. I'm supposed to go display 0, then display 1, then display 2, then display 3. So this time A would be 1, 1, 0, 1. And then from there, I'd go to, my next state would be state C. And state C is supposed to be a 5. And again, this is not what y'all's are. I'm making y'all do a little bit of the work on your own. So a 5 is like that. And so that would have C equal to, the only ones that aren't zeros are the second one. So that's a 0, 1, 0, 0, and then that one, and then 0, 0. And then A would equal 1, 0, 1, 1. And then from there, I'd go to state D, and then state E, and then state F, and then state G, because I have 1, 2, 3, 4, 5, 6. I'm supposed to have 8 states. 1, 2, 3, 4, 5, 6, 7. I guess H. And then from H, I go back to A. So my state diagram is really pretty simple. It's just a loop, and that's what counters are. Counters they just loop. So it's, you go from one state to the next, to the next, to the next, to the next, and then back to the beginning. So this has, let's say that I had my count sequence only had 6 states. Then I need to figure out 2 raised to what number is greater than or equal to 6. And that would be 2 raised to the 3rd is the smallest number that's greater than or equal to 6. So that tells me I need to have 3 flip-flops. And it means to define my states, I need 3 binary numbers. Now, if I had 6 states, I would have to take care of the fact that there are really 8 binary numbers that have 8 numbers that, there's 0 through 7 are numbers that have 3 binary numbers. Y'all know what I'm saying, right? Yes. Okay. I would have to be very careful to account for the extra 2 that I'm not using. Y'all's lab has 8, so you'll be using all of them, so that's handy. Okay, so the pre-lab is really very easy, but I don't recommend that you stop with that, because the pre-lab says create a state diagram, choose a minimum number of flip-flops to realize all the states, and construct a state assignment. And so the state assignment would be that I assign, so I had my state diagram up there, and I'd just assign A to be 0, 0, 0, B to be 0, 0, 1, C to be 0, 1, 0. Now, you can define them however you want. But I would recommend that you have this order be, take advantage of the fact that Verilog can count on its own just by adding 1 each time. That's what I did at the very beginning. And so you have kind of a built-in counter. And so if you use that to match up with 0, 1, 2, 3, and you just progress like this, that will make your life easier. You'll see what I mean when we get to the coding part.
In Verilog, if you add 1 to 7 in this case, it just goes back to 0?
Yep. Handy. Yep. Let's see.
Miss Rebecca,
Yes.
what is the C doing in the state diagram again? Is that selecting what part of the segment you're going to light up?
Correct. So
Okay.
it's you are sending it all 7 of the values at once. So when we look at the Verilog, so when we go to the constraint, this is assuming that instead of seg you had C here, because that's all the examples use C. So that's why I use C. So these were C. And rather than sending them one at a time, you can send them all at once, and you would do it by saying C equals, and then you give it, and this is C0, and this is C1, and this is C2, and so forth. Okay, so what I'm going to do now is I'm going to go to Verilog. I happened upon version 2, which is the one that I have that uses the buttons. Oh, it's already up to date. Excellent. Okay, so I will just program the board so you can see what this is supposed to look like. I don't know who just left, but you know, the good part is coming up, and that's the coding. But yeah, that's it.
And we lost your share screen again.
Yeah, I meant to do it this time. This time it was on purpose because I wanted to show you the board.
Gotcha.
So here's the board upside down, and this one, my cable is just too short. So this one is using the button to be the clock. Which button is it? Oh, there is also an enable. You're supposed to have an enable. So that is key. Mine is not enabled, and so I have one switch that is the enable. So I need to turn that switch. I made my switch this one, so now it is enabled. And I will go back and show you. And now when I press the button, it advances to the next display, and then with the next number, looks like I skipped one. No. And it doesn't matter really if you go right to left or left to right. That's not that important. Okay, so that's what it's supposed to do, but I'm glad that I remembered the enable. So I'll go back now. And let's talk about how you're going to code this. So before I get to the, can you see my screen again? Good.
Yes.
Okay. All right. So any questions before I go on to the coding part? I strongly recommend that you do as much of this as you can before you get to lab. Just do it in a text file, or if you have Notepad++, or if you have Vivado itself, that's good. So you're going to have
I have a question.
Yeah.
I was wondering on the state diagram, what is the A value?
The A value is telling it what display it's going to be on. So you have the displays 0, 1, 2, and 3. And so the A tells it which display it is. So for example, when I am telling it what state to go to, when I am defining a state, and this is going to be in a case statement, so case 0, 0, 1, for instance, then I would tell it whatever my variable name is for my string, and then I also would tell it which display I wanted. So if I wanted display 2, I would put a 0 in spot 2. If I want to display 1, I'd put a 0 in spot 1. And whenever you do this, you are going to have a begin and an end, because you will have more than one statement in there. So that's what the A is. So in your Verilog, you're going to have the following sections. So now you only have 2 inputs, enable and clock, and that's it. And you'll have 2 outputs. I called mine seg, and if I was smart, I would have called the other one an, just because those match the templates. And that's it. And so your input is en and clock. Now, you will want to map your enable to any one of the switches you want. It does not matter which switch you use. You just have to remember which one it is. Being lazy, I chose the one that was at the top, and so that's going to be your enable. And so don't forget about that the way I did and say, oh, it's not working. And then to have the button act as the clock, you'll also need to have these lines, which I think are in that, no, this is not in the template. So this, you'll have to get this from, Vivado Basics, yeah. Which is here.
It's at the bottom.
Is it in lab resources or lab assignments?
Assignments.
And it's here. And I think I put a link to it also in the lab, in lab 8. I think there's a link as well. It is.
Where's the last slide? What is it?
Yep, right here, to use a button as a clock signal, right there. So that's what you need for that. And you'd map that to your clock. So I called my clock CLK. You need to have CLK there. And okay, and then your output. And notice how the Notepad++ helped me. I typed output, and it didn't make it blue, and so it reminds me that there's an error. And I'm going to define it as reg, because I'm going to change it in an always block. Notice this one is in the opposite order. Just that's the way it makes sense to me. Okay, now you are going to need to have some other things as well though, because you'll need to have something to stand for your states. And so I strongly recommend that whenever you do a finite state machine, you use 2 always blocks. One always block tells you what the next state is going to be. The other always block advances you to the next state. So I called mine Q because that's what we use all the time. So reg 2:0 because I needed 3 bits to define the states, Q. And then I also had reg 2:0 next Q. Because in the first always block, you tell it what the next state is going to be. That's next Q. And then in the other always block, you actually define it. And let's see. Okay. And then from here, I think I initialized the Q to be B000. I've noticed a lot of students do like to use the parameters so that you don't have to use the binary numbers. So if you want to, see if I can remember how to do that. I don't use the parameters because even though it might make it easier to read, it's like one extra step. But, and yeah. Okay, so here's how you would do the parameters if you wanted to use them. And so you can set them up like this, and then you would need one more because yours would actually have an H. And then you don't have to use the binary numbers anymore, you can just use the parameters. So then from here on, once you do this, you can just use A, B, C, D, E, F, G, and H. So I'll copy this. So there's commas in between all of those and then a semicolon at the end. Oh, this is a lot easier to read than the projector was, I think, yeah. Okay, so then you're going to have your first always block. And this, you're going to say anytime Q changes or enable changes, you want to set a new value for what the next Q is going to be. Now, it's easy because they're going in order. And so you don't have to do this the way I do it, but have a case statement. I don't know if I need a begin and end yet. I don't think I do. So case Q. So this is based on what state am I currently in? I'll go to the next state. So Q, so I've got the parameters here, so I might as well use them. A, and then I'll have a begin, and I'll say C equals, you don't need the non-blocking, but I usually use it anyway, so you could use an equal sign if you wanted to. C equals 7B, and then whatever your string is here, A equals whatever display you want it to be on. And then you tell it what your next state is going to be. So next Q is going to equal Q plus 1. You take advantage of the fact that it is a binary number. And so if Q is 0, 0, 0, then 0, 0, 0 plus 1 is 1. And you can do this for every state, even state 7. So for every state, all you have to do, and actually we could, lazy. I like lazy. Okay. I'd have to put a begin and end in here. But. Because no matter what the state is, I get down to H, then I do H, and then these should be indented. End case, but still inside the always block. I can just do this once. Here I do need to use a non-blocking because I don't want to change it until it gets out. and I can just do it once, because for every state, I'm doing the same thing. For every state, I'm saying the next state is one more. That's why I recommend that you use the numbers in order, 0, 1, 2, 3, 4, 5. You don't have to. You could make them whatever you wanted, and then within each case statement have them equal something else. Okay, so then, and then you can end that always block. And then, oh, what I forgot, the enable. If enable. Actually, I'll put that in the next always block. Where do I want it? I want it in the next always block. So always at pos edge clock. If enable, Q becomes next Q. End module. And let me make sure I didn't forget anything. See, I could have saved myself, gosh, minute of typing by putting that next Q at the,
In the one that you're writing,
Uh-huh.
in the top one, didn't you put Q equals Q plus 1?
I did.
Should it be next Q?
It should be, yes, it absolutely should be. Next Q, because I don't want to change Q until I get to here. Yes. Yep. All right, so let me go back and look at the lab and see if there's anything else I'm forgetting. If you want to stick around, I'll show you how to do it with a real clock, and if you are not interested, my feelings are not hurt. But let me check and make sure that I'm not forgetting anything. You need to show your lab instructor the state diagram. You need to write the constraints file. You know how to do that. I didn't find a test bench particularly helpful on this one, but if you wanted to, you could. You program the board, you demonstrate it, you say, look at me, I got it done in no time, I'm brilliant, and see you guys later. And don't tell them that, like, SI really was helpful. You know, you don't have to tell them that. Yeah, okay. All right, any questions before I go on and do the clock part? All right, so I am going to stop.
Rebecca?
Yeah.
So in you have the always block, and then you do each state, and then you can just say the next Q is Q plus 1 at the end of that always block?
I can, yeah, because it turns out that and this is only because of the way we defined the states. We defined the states so that for every state, the next state is one more than it. Usually that's not the case.
Gotcha.
Usually you would have to do this within each case.
Gotcha.
Yeah.
Thank you.
Mm-hmm. Okay, any other questions? No? All right, I'm going to stop this recording and I'm going to start another one to show you how to use the clock if you are so inclined and if you want to leave.